Hi there, welcome back to Triplicate, and yep, moving on with our little LED based neon. We got it working kinda, but not exactly as we wanted. So here we have 0 volts and it's off, so we turn her up. 3, 4 volts. And we go 4.9, it turns on. That's pretty close to what we want, but if we wind it down we want it to turn off. I can't remember what we set it to, 3.5 or 3. Nah, it doesn't, and it just gets dimmer and dimmer and dimmer, and it's not, oh, it has turned off there, but it's basically not doing what we want it to do. Okay, and I had a poke around and I decided our problem was our voltage reference, which is here, which is a Zener diode. And there are two problems with this Zener diode. Firstly, we wanted it to turn off from 3 to 3.5 volts, but that is a 3.9 volt Zener, so obviously once the supply gets down to below 3.9 volts, yeah, it's not going to do its job, is it? It's just going to turn off completely. And the second problem is to do with Zener diodes, the nature of them and the job they do, and it's a problem I always anticipated happening and hoped I'd work around. Okay, so power equals voltage time current, and we want to know the current we should put through this Zener to get it to work at a reasonably in its working area. So I equals P over V. Well, it's rated 200 milliwatts, so let's call the power 100 milliwatts, or 0.1 of a watt, and the volts is 3.9, and we're going to call that 4. Just for ease of mental arithmetic, so that gives us I equals 100 milliamps over 4 is 25 milliamps, and we said, I know this is arbitrary, but it's got to be something like this, we don't want the circuit drawing more than a milliamp from our supply when the LED is off, so that is patently obviously too much. Okay, and here are the curves for Zener current versus voltage, and this one's our Zener. You can see, yeah, below 10 milliamps they are not very good at all. So do we have an alternative to using a Zener in this application? So here we have a power supply connected through a 12k resistor, because it was what I had lying on the bench, through a forward bias, that's a 1N4148, just a little signal silicon diode. So let's see what that does. So we want to know how it behaves between 3 and 6 volts basically. That's the operating range of our circuit. So it's hard to get this knob round here. So that's 0.689 volts at 3 volts power supply, and if we wind this up to 6 volts, .714. Well, I reckon that range is going to be enough for what we want to do. We're not building a power supply, we don't need a precision reference, so that'll probably work. Okay, and just quickly, should we get a kind of error over the range? So the error equals 0.714 minus 0.689 over 0.7. We're just going for a approximate value here. 0.714 minus 0.689 divided by 0.7 equals 0.035, etc, etc, is approximately equals to 3.5% error over the entire operating range of the circuit. That's good enough for what we're doing. It really is. Okay, here we go. Here's my hacky little program just to solve the equations and get the resistors out. In this case R3, R4 and R8. And I put our new, what we call Zener voltages, is reference voltages in, and it will find, you put one of the resistors in and it'll find the other two to suit. So we go through here and it does it the triplicate mathematics way of just ramming tons of values in and finding the best. So here we go. So if we look down here, our low threshold we put at 3.5, our high threshold we put at 499. We put the V Zener, or the reference voltage, into 0.7 in the middle of the range we got. So R1 we set to 10, so R2 has come out at 57, and R feedback 134. So the resistor numbers are different. So in the program that's R1, that's R2 and that's RF. So then I came back and I put preferred values of 10k, R2 56k and RF 120k I think, and we can run that and it'll see what we do. And I've tried it with both ends of the scale of the VZ, the reference. So at the low end the reference will be low, so VL is about 3.3, and if we look here VH will be just over 5, so that's near enough for me. So I will get our little circuit board and I will change our resistor values and we will see if it works any better. Okay, so got my diode in. Not without a struggle, because there's a very faint line marking the end, and once you've soldered it and got some flux over the top of it, you can't see it. So I've got it in the wrong way around first attempt. Anyway, she's working now, and rather than try and point the camera at the power supply, I've got 2 meters going here. We'll move that random wire. So that's 3 volts in and 0.53 volts across our diode. Okay, so we wind it up to 6 at the other end of our range. There we go, that's 599 and that's 5.565. So let's call that point 0.565 minus 0.53 divided by about the middle of that, which is 0.548, yeah, 0.548. We're only getting an approximate. So that's giving us a 6.4% error, which is a bit more than we had with our original diode, but it's fine and it doesn't go all that range, so it's probably nearer 5% over the range we're using, which is good enough for what we're doing. Right, so now I need to change those 3 resistors to reflect the new reference. Oh, and I've shorted out here the base of the transistor just so it doesn't turn the LED on, just in case that confuses the issue. So I will fire the soldering up and make those changes. Okay, after a considerable amount of backwarding and forwarding with my little resistor calculating program, as you can see with the scribblings out on here, that resistor is 10k, that resistor is 82k, and that resistor is 150k. And that one, I couldn't find a surface mount of that value, so it's got a through hole tacked on the top. It's a test board, as I've said before. Right. So here we have 2 meters. This one is measuring current draw, and this one is measuring voltage across the circuit, and it's 3 volts, and you can see the LED's off, so it's turned out, and it's drawing 0.33 of a milliamp, which we decided 1 milliamp was the maximum we wanted, so that's good so far. So let's crank her up. Okay, so we're on 5 volts, 5.1, 5.2 in fact volts, 5.3 volts, 5.4 volts, and we're still just drawing 0.58 of a milliamp, 5.5 volts, and on it comes. That's a bit higher than we wanted, but for now I think we're just going to progress with what we've got and see what happens. Okay, we now start turning it down again. Okay, 3 volts. Okay, that's gone off 3.3, again a little higher than we wanted. I will review the values, but that is going to work for now to test the functionality. Okay, what we also want to try here is we have our Zener. There you go, it's a Zener diode to protect the circuit, and I want to get it will protect the circuit, and it won't draw too much current when it's not protecting the circuit. So that's the positive end. So I'm going to clip that on there like that, and that's the negative end, and we're going to clip that on there like that, and we're down at nearly the minimum voltage we're going to. So it's not gone up at 3 volts, so we're going to pull the voltage up. Okay, that's just about a trigger, and it is a bit high, but it's still lower than a millivolt, so I will take that. And we turn it on, and it's 17 odd milliamps, that's what the LED is drawing. And if we continue to turn it up, yeah, it's then kind of protecting the circuit, and 25 milliamps, and then it's gone over 40 milliamps. So it gets up to 5.9 volts, and it'll pull it down and empty whatever capacitors are driving it before the circuit comes to any harm. So I am happy with that also. So shall we connect up a resistor and a capacitor and see if we can make an oscillator. Ooh. Okay, apologies for the spaghetti. The power comes in here from the meter that's measuring current. Goes through, that's 3K 3 resistor via the LED neon circuit to ground, and there is a 1000 microfarad capacitor there across our LED neon. Simple circuit, should just oscillate, should just blink regularly. So we have a supply voltage, which at this point you're taking my word for, set to 5 volts. And because the circuit's drawing a little bit of a current, we're only getting 4 volts across the circuit. So we are going to increase the supply to 7 volts. You're taking my word for it here. And again, the capacitor's charging up, the voltage gets to 5. 7.5 volts, the voltage has come up a bit further. Oh, there it is, 7.9 volts. It'll just about creep up to the trigger voltage. And we said the circuit was going to run at 12 volts. So let's wind it all the way up to 12 volts. And yep, she's blinking nicely. And interestingly, the whole thing is drawing a fairly steady 2 milliamps. Anyhow, so we have a working LED neon which is now replicating that thing. So I think that's probably about all we can do with one circuit. So I shall now get my soldering iron out and build, I don't know, another 2, another 3, and we'll spare you the pain and heartache of surface mount soldering. Yeah, it's not that bad. And we will have a look and see how we can connect them together. Okay, well I think I'm going to call it for this video. Leave it here and we'll pick up the LED Neon Blinky project again when I have some more boards built and we can start to connect them together, which should be interesting. So until then, it is goodbye from Triplicate. Goodbye.